I am on a mission to transform the 406mm telescope at the Rice Creek Field Station Observatory into a state-of-the-art research facility. This is my story. Objective 406, Episode 2, the problem statement. It is obviously important to have the right solution for the right problem, and that's what we will look at in this episode. The distance between the observatory and the control room is just about 40 feet door to door. That becomes a significant consideration when we look at the difference between RS-232 and the USB cables. Main reason why telescope manufacturers still rely on RS-232 is the distance of 50 feet that it can accomplish versus USB, which is about a third of that. 50 feet is cutting it close here once we get to the middle of the observatory. However, RS-232 over Cat5 can go as far as 3,000 feet or a kilometer. Inside the dome, this is the Smart Dome controls from Smart Dome from Astronomical Consultants and Equipment. The main switches are reverse and forward, open and close, and up and down. In addition to this control box, there is another emergency control box built into the moving part of the dome that can be used to stop the dome in an emergency or move it. The orange path below the dome are the live wires, and I was instructed not to touch them, which will be a good idea, not to get electrocuted. Above the telescope is the slot that opens and closes, and the daylight that you see at the top is the reason why the telescope remains covered with a very large plastic bag when it is not used, to protect it against water seepage from rain during high wind storms. And yes, I believe that little brownish spot in there is a beehive that I'll have to take care of, given my extreme allergies to bee sting. The Meet 16 telescope itself, it's an LX200 advanced comma-free 18 volt DC input. You can see the RS-232 port and the Handbox AutoStar 2 controllers. This is not my first exposure to the Meade LX200 ACF. 2 years ago I bought one. It was a 12-inch LX200 ACF computerized telescope, and I looked forward to using it and enjoying it as a replacement to my 8-inch Celestron Edge HD that was on a CJAM mount. When I turned it on, align on home, it started finding home, and then the sinking feeling when motor failure was displayed. We're talking about literally the very first time I turned it on. The motor stalled after moving a few inches and it declared motor failure. I spent the rest of the day on the phone with High Point Scientific and Meade, and by the end of the day, that beautiful telescope was in the box being shipped back because of the motor failure. Unfortunately, no one else had any Meade telescopes in stock, and I ended up with a Celestron Edge HD 11-inch instead of the Meade. So this is my second exposure to Meade telescopes, and obviously I'm a little bit shy given my unfortunate experience with my own Meade telescope. Fortunately, in the corner of the observatory, there was a Meade 8-inch LX200 ACF sitting on a cart that I can use initially before I start swinging around the 250-pound telescope And that gave me some sense of a feeling of security that I can do all my testing on the 8-inch before moving to the 16-inch telescope. Hence, our problem statement. The advanced course in engineering presents a repeatable and time-proven methodology to solving problems with open-ended problems that do not have a unique solution. First step is to formulate a clear problem statement. What are we trying to achieve? The second step is to make reasonable assumptions. Third step is to apply tools and techniques. And then finally, solve the problem to a certain depth. We are not going to conduct any risk analysis in this case. And finally, we do not have a set time frame to deliver the solution, so I will not worry about the last two steps of the ACE methodology to solving problems. The clear problem statement answers the what. What are our end result objectives? As I see them, accurate targeting of deep sky objects with precise tracking for many hours. This is going to require, obviously, slaving the dome to the telescope. We have to assume a trade-off between low noise and long exposure imaging versus high resolution color imaging. At this early stage, I do not anticipate using filters for red, green, and blue, or for hydrogen alpha, oxygen 3, and silicon 2, but rather I intend to use a color camera initially. The secondary objective is planetary imaging. The reasonable assumptions here seek to bound the solution space and not trivialize the problem, and that has always been a challenge. The first big assumption is that the Meade 8-inch is functionally identical to the Meade 16-inch. We're not talking about the 3 times difference in weight or the 2 times difference in aperture, but rather the functionality, so that whatever I test on the 8-inch, I assume will work on the 16-inch. We will be targeting slow-moving objects. I have no plan at this point to target fast-moving satellites or aircraft in the sky. I also plan to focus on nighttime imaging initially, so that we are not looking at solar imaging. And finally, fair weather observation. That's going to be a reasonable assumption that we're not going to operate it in high wind or extreme weather conditions. Finally, the assumption of compatibility with common astronomy tools. And by common astronomy tools, I mean the ASCOM, the Astronomy Common Object Model. Tools and techniques here assume that I will use tools and techniques that I've already used over the past several years of astrophotography and astronomy, and that I do not intend to learn new tools for this objective, given the steep curve of learning new tools. For the graphical interface, I will look at NINA, Stellarium, and Starry Night, and I plan to use plate solving for accurate targeting, assuming that the telescope is not going to give me the accurate targeting. I do not know how carefully polar aligned it is, and I do not know how well the 16-inch Meade will track. So plate solving is going to be my fallback. I have going to have a choice between CCD and CMOS cameras as well as spectrographs. I will be testing these to decide on the best choice. Given an aperture of 16-inch, I'm going to require a high resolution in order to achieve plate solving. A lower resolution camera of 1 megapixel or 2 megapixels may not cut it at this point. Ultimately, a decision on whether to use the main scope for guiding or whether we need to put an auto-guiding scope on top of it with its own camera. And finally, the choice of imaging software. I have significant experience with SharpCap, NINA, and Zoo, so it's going to be a choice among these to see what will cut it for us. So my work is cut out for me. and I look forward to starting to tackle these problems.